Hi, this lecture is covering derivatives for the basic logarithmic and exponential functions. Okay. Up to now, we've pretty much been only to use functions that have simple derivatives using the power rule, constant rule, sum and difference. So, like I said, time to start expanding our library. So I want to look at the exponential function. F of x equals e to the x. We want to find its derivative. Right now, we don't have any formulas that would allow us to do this. So pretty much we're stuck using the definition of the derivative. Okay, so using our definition of the derivative, and I'm going to take the derivative of the function e to the x. I need to take, whoops, wrong pen. Let's try this. There we go. So I'm going to take the limit, so f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h, so this is going to be e to the x plus h, minus f of x, so minus e to the x all over h. Now the first thing I try to do is substitute in a 0 for my h's, but then I get e to the x minus e to the x, which is 0, so I get 0 over 0, which is the indeterminate form. So I have to be able to manipulate this in some way. First I'm going to do is I'm going to go ahead and use my product rule to break up this term right here. So remember that when we're multiplying, we add exponents. So if we're adding exponents, that means we are multiplying them. So I'm going to take that term and write it as e to the x times e to the h. And then everything else will remain the same. Okay. Now I have a common factor, e to the x. And I'm going to factor out my common factor of e to the x. The other thing I'm able to do is, because I'm looking at the limit as h approaches 0, e to the x isn't affected by h, so I can factor it out and bring it in front of my limit. So now what I have is equal to e to the x times the limit as h approaches 0 of e to the h minus 1 all over h. And if you recall from last class, this limit right here was equal to 1. So now we have e to the x times 1, which is e to the x. Therefore, the derivative of e to the x is e to the x. Okay, so now we have a formula that we can use for determining the derivative of the basic exponential function. Okay. We can go through a similar argument or proof for finding the derivative of the natural log, but I'm going to spare you all that. Okay, so I'm just going to get to the punchline. For g to x equals the natural log of x, the derivative is 1 over x. Notice that once you take the derivative, you no longer have a natural log in it. Okay, so these are our two rules. In the textbook, you're going to see additional rules for other bases like base 2 and base 5, or log base 2 and log base 5. We're going to skip those and just stick with base e. Okay, so let's put this into use. First thing I want to do, find a couple derivatives using our new properties. So for this one here, I have m of x is equal to 4x to the third plus e to the x. All the previous properties and rules we've learned still apply, meaning that I can take the sum of the derivatives. I can multiply it by a constant. We already know how to do that one. So we are going to go straight to m prime of x is equal to the derivative of 4x cubed is 12x squared. And then the derivative of e to the x is, that's our new rule, dun, 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 e to the x. And there you go. Okay. So for our next one, I have 500 times e to the t. Remember that we have the constant rule. So multiplying it by 500 is the same thing as just taking 500 times whatever the derivative of e to the t is. So r prime of t is going to be equal to 500 times, what's the derivative of e to the t? E to the t. Alright, simple enough. Oh, logarithms. These get a little bit different, not much. Similar example right here. I've got the sum of a couple terms. So taking the derivative of each term, we'll have c prime of x is equal to the natural log, the derivative of 8x cubed is going to be 24x squared plus, and now we use our new rule, the derivative of the natural log of x is 1 over x. Okay. And s of t, here's another instance where I am using my constant multiple rule. S prime of t is equal to 24 times, now what is the derivative of the natural log of t? It's just 1 over t. Okay. And this should be cleaned up a little bit, so I'm going to rewrite that as 24 over t. Okay, now you need to practice some. Okay, I'm going to work out each one of these, but I would strongly recommend that you hit the pause button right now and try these on your own before watching the solution. Okay, here we go. Hit that pause button. First example, I have 8 e to the x. Using my constant multiple rule, we get f prime of x then is equal to 8 times the derivative of e to the x. So my answer is 8 e to the x. The next example, n of z. I've got a lot going on here, a lot of ugly fractions and everything else. 2/3 pi, that's a constant. And the derivative of any constant is always going to be 0. So n prime of z so far then is 0 plus, and then how about 1/7 times e to the z? Well, the derivative of e to the z is just e to the z, so this is 1/7 e to the z. And again, just to clean this up a little bit, we can rewrite it, go to the 0, 1/7 e to the z. Okay. Alright, now these are getting a little bit tougher. Again, before watching me work these out, hit the pause button, try it on your own. Now in this one we have two options. So some students prefer to distribute the 50 and then take the derivative of those terms. We do have the option of treating this as a constant multiple, so we can take 50 times and then whatever the derivative of these two are. So you work it out either way. Actually, it's probably a good idea to work it out both ways. Okay, so I'm going to start just by leaving it as it is. So h prime of x is going to be equal to my constant 50 times. And now inside the parentheses I'm taking the derivative. So the derivative of e to the x is e to the x. And the derivative of 10x is 10. There you go. If you need to simplify this, some would consider it simplified because it's factored out, or maybe you'd want to distribute the 50. And like I said, an alternative way of doing this one is you could go ahead and distribute the 50 first. So you have h of x is equal to 50 e to the x minus 50 times 10, so we get 500 x. And now taking the derivative of each term here, 50 e to the x gives me 50 e to the x, and the derivative of 500x is 500. And then if you distribute right here, we get the same thing. So these are equal to each other. Okay. This one here. We know the 5 over x. We've seen that one before. We're going to use properties of exponents to move that up. So the first thing I'm going to do is rewrite this algebraically. So f of x is equal to 16x to the third plus 5x to the negative 1, and then this e to the fourth. Now I can go ahead and take the derivative of each term individually. The derivative of 16x to the third gives me 48x squared. And then here, same thing, I'm going to bring down my exponent and then decrease it by 1. And how about the derivative of e to the fourth? Did I get you on that one? Remember, e to the fourth is a constant. You can plug that into the calculator, you get a real number. So that derivative is 0. So my final answer, simplified form, then of course I would not include the 0 with it. Okay? Alright, we have a few more examples we're going to work through. These get a little bit trickier. The natural log of x to the fourth, we don't know how to do that one. We can only take the derivative of the natural log of x right now. Next class we're going to learn some other techniques, but for right now we can do the natural log of x and that's it. So I need to have a way of rewriting this. So here we go back to our rules from algebra. We said, alright, well, we know that if you have a logarithm with an exponent, that exponent comes down as the coefficient. So this can be rewritten as y is equal to 4 times the natural log of x. And now I can go ahead and take the derivative the same way we did earlier. So y prime is equal to 4 times, and whatever the natural log of x is, 1 over x. Again, just to clean this up a little bit, I'm going to write it as 4 over x. Okay. How about q of t? What can I do with this one here? Okay. I've got 4 over t. This one here does not require exponents. It doesn't require the logarithmic function. It's kind of like a trick question. A lot of times when students see this 4t to the negative 1 or 1 over t, they start thinking, oh, that's the logarithm. Once you take the derivative, that's what you get, but if you're starting off with this here, it's just like back in chapter 3. So q prime of t is going to be equal to negative 4t to the negative 2. And I'm happy with you leaving your answer that way. If you prefer, you can rewrite it as negative 4 over t squared. But again, I'm happy right here too. Okay. Now we're going to look at a few applications. First thing I want to do is find the slope of a tangent line. Okay. So keyword here is tangent line. And how do you find the slope of a tangent line? That's right, you take the derivative. So the slope of the tangent line is going to be equal to f prime of x. Or in this case, since we want to know the slope of the tangent line at 1, we have to evaluate it at the x value 1. Okay. So now we have to take the derivative of this new function. So f prime of x is equal to, the derivative of 3x is 3, and then how about 5 natural log of x? We've got 5 times, and then the derivative of the natural log of x is 1 over x. Okay. We need to find the slope, so I'm going to have to evaluate this expression at 1. It's not too complicated. You can leave it as it is, or you may want to simplify it first. So slope is equal to f prime of 1, which will be 3 plus 5 times 1 over 1. So we end up with the slope is equal to 8. Okay. Our next question, very similar, but this time we're asked to write the equation of the tangent line, which same function, and pass us through that point there. So remember, to write the equation of a line, we're going to start with a point slope form, which is y minus y sub 1 is equal to the slope times x minus x sub 1. And we have to plug in numbers for y1, m, and x1. x1 is going to be given. This is the point x equals 1. The y value, we use algebra to find the y value. Y is always equal to f of x. In this case, it'll be f of 1. And then the slope of the tangent line, as we just discussed, the slope of the tangent line is equal to the derivative, again evaluated at a particular function value. Okay, so I know my x value. We just computed the slope. I need to go ahead and find my y value. So let me do this up here over on the side. So my y value is equal to f of 1. So I get 3 times 1 plus 5 times the natural log of 1. You can plug this into the calculator, or maybe you remember that the natural log of 1 is 0. So we get 3 plus 5 times 0, or my y value is equal to a 3. Okay, I'll take all this information, plug it in my formula. So I have y minus 3 is equal to the slope, which we found on the previous page was 8. So this is 8 times x minus 1. I'm always going to ask you to write your answer in the slope-intercept form, so I will distribute the 8 and then add the 3. So y minus 3 is equal to 8x minus 8. Adding 3 to both sides, y is equal to 8x minus 5. And there is the equation of the tangent line. Okay, here we go. Last example. Yeah. An experiment was set up to find the relationship between weight and systolic blood pressure in children using hospital records for 5,000 children. The experimenters found that the systolic blood pressure was given approximately by P of x X is between 10 and 100, and P of X is measured in millimeters of mercury, and X is measured in pounds. What is the rate of change of blood pressure with respect to weight at the 40-pound weight level? All right, before we try to answer this question, we need to figure out, what our formula is, what it's measuring, what our variables represent, and then we'll have a better idea of what we're trying to find. Okay, so first I want to point out that we're looking at P of X, and that this is measuring systolic blood pressure, and it is terms of measured in milliliters of mercury. So P is equal to the systolic blood pressure. So I'm just going to put down blood pressure. And it is in millimeters of mercury. Okay. And how about our variable X? X is being measured in pounds, and it's the weight of the child. So X is equal to the weight, and it is in pounds. Okay. So now I'm ready to focus on the question. We're asked to find the rate of change. So that tells me to take the derivative. So I want the rate of change of blood pressure. So I want the rate of change of P with respect to weight. So that's with respect to the variable X. So I am looking for P prime of X. And if I want at the 40-pound weight level, I'm really looking for P prime of 40. That's going to be my answer. Okay. So what is P prime of X? Well, we're given our formula up here for P of X, and this is like one of the examples we've already worked out. You have the option, if you want to distribute the 17.5 first, and then go ahead and take the derivative by each term, certainly that's something we can do. So let's go ahead and we'll work it out that way this time. We'll go ahead and get P of X then is equal to, let's see, where can I write it? Got P of X is equal to 17.5. That's not going to fit in there. Let's try one more time. Here we go. So P of X is, I'm going to distribute 17.5 plus 17.5 natural log of X. Okay. Now I'll take that derivative. The derivative of 17.5, that's a constant, so it's just a 0. And then over here on my second term, I get 17.5 times, what's the derivative of the natural log of X? It's 1 over X. So I'm going to clean this up. P prime of X is equal to 17.5 over X. And now evaluating my derivative, when X equals 40, that'll give me the 40-pound weight level. I get 17.5 divided by 40, which is going to be equal to 0.4375. So the rate of change is going to be 0.435. This is millimeters of mercury per pound. All right. That's it for this section. Stay tuned for more.